Two things to talk about today. First, let's go back and think about graphs of velocity versus time. And imagine the simplest possible case, a constant velocity. And the velocity stays constant during this time interval that we'll call delta t. And we'll just call the numerical value of that constant velocity vc, c for constant. And now remember our definition of average velocity: displacement divided by the length of time it takes to make that displacement. That's average velocity. But since the velocity is constant, no matter what numbers you use to calculate this thing, you'll always come up with the same value, vc, because constant velocity means there is only one value ever for the velocity, vc. So in this case, we can simplify a little bit and say that average velocity is really just the same thing as the numerical value of that constant velocity. Now, take this equation, displacement divided by the length of time it takes to make that displacement equals vc. Multiply both sides of the equation by vc, and then we have displacement equals the time interval times vc. But look, this time interval corresponds to this length on the graph, and vc corresponds to the height on the graph, the height of this rectangle that's formed by the velocity line and the time axis and the initial and final times in the time interval. So the displacement, in other words, is equal to a length times a height in the velocity versus time graph. This length, this height. But of course, this length and this height is just the area of this rectangle. So we have a conclusion. Displacement is just equal to area in a graph of velocity versus time. Area between the time axis and the velocity line, and bounded by the beginning and ending times when you were watching the motion. And the important thing is that this relationship, displacement equals the area on the velocity versus time graph, is true no matter what the velocity line looks like. It doesn't have to be straight. It could be a complicated kind of velocity line, but it's still the case that this area between the velocity line and the time axis is equal to the displacement that happened. One qualification here that one needs to remember: all this is true, displacement equals the area, if the velocity is positive. And we know that if velocity is positive, that's because the displacement is positive. And area is always a positive number. In plain old Euclidean geometry, we don't have negative areas. So this is a positive number, and that'll make the displacement positive. Positive displacement is what you get if the velocity is positive. If the motion is always in the positive direction, the displacements you get from that motion are always positive. Now, let's look at a slightly different case. What happens if the velocity is negative, not positive? So our simple velocity versus time graph will look like this. A a negative constant velocity, and we'll say that the numerical value of that negative constant velocity is minus VC, the negative constant velocity. The number VC itself then is positive. So we get the negative velocity by explicitly multiplying VC times minus 1. And here's the length of time. Delta t is the length of time when the moving thing had that velocity of minus VC. And it is still the case that displacement divided by the length of time it took to make that displacement is equal to the average velocity, but in this case, average velocity is going to amount to the same thing as the actual constant velocity minus VC. And so displacement is equal to the time interval times minus 1 times VC. But again, delta t corresponds to a length on this graph. VC corresponds to a height on this graph, a distance along the horizontal axis. So we can think of this delta t as simply minus 1 times length times a height. This length times this height is just the area of this rectangle. Or in other words, it's the area between the velocity line and the time axis and between the initial and final times in the time interval, delta t. So, displacement now, when we had a negative velocity, is minus 1 times this length times this height. This length times this height is the area of that rectangle, area between the velocity line and the time axis. So if you have a negative velocity, then displacement is minus 1 times the area, minus 1 times the area. And again, that's true no matter what the area between the velocity line and the time axis looks like. When the velocity is negative, the motion is in the negative direction. The value of location number is always getting more and more negative. As time goes by, later locations are always more negative than earlier locations. So displacements are always negative. And so to get the negative displacement, you have to multiply minus 1 times the area between the velocity line and the time axis, because area itself is always a positive number. Let's look at an example of that. Remembering that if the velocity is greater than 0, then that implies displacement equals area. If velocity is negative, if motion is in the negative direction, then that implies displacement you could calculate just by finding minus 1 times the area. So let's say we have and remember these are areas on a velocity versus time graph, not position versus time. Let's say we have a velocity versus time graph that looks like this. And we'll do it with numbers this time. Time in seconds and velocity in meters per second. And let's say here we have 4 meters per second. And down here we have, let's say, minus 2 meters per second. And let's say that the velocity is changing. Velocity starts out positive, but slows down until it's 0. This is 1 second, 2 seconds, 3 seconds, and 4 seconds. And now, continue this line. So now we have negative velocity. And then the negative velocity becomes minus 2 meters per second at the 3-second mark. And then goes back to 0 at the 4-second mark. So, use the basic principle. The grand total displacement during these 4 seconds is, of course, the displacement that happened during the first 2 seconds plus the displacement that happened during the last 2 seconds. Displacement during the first 2 seconds happened when the velocity was positive, so that displacement is just the area between the velocity line and the time axis. It's a triangular area, and you can always calculate the area of a triangle as 1/2 base times height. So this area is 1/2, and the base side of the triangle is 2 seconds long. And the height of the triangle is 4 meters per second. And that comes out to 4 meters. Right? A time times a speed will always give us a distance. Now, the displacement between 2 and 4 seconds is a displacement that happened when the velocity was negative. So when we calculate the value of that displacement, it's going to be minus 1 times the area. Minus 1 times the area between the velocity line and the time axis. So again, it's a triangular area. So 1/2 base times height. The base, again, 2 seconds. And the height is this much, which is just 2 meters per second. This length is 2 meters per second. And that comes out to just minus 2 meters. So the total displacement from 0 to 4 seconds is just 4 meters minus 2 meters, or 2 meters. And we'll see a lot of other situations that use this idea. On a velocity versus time graph, there's a relationship between area, between the velocity line and the time axis, a relationship between that area and how much displacement you get during that time. Okay, that's one idea. The other one is not really related to this. It's quite different, but it is related to other things that we have talked about. Acceleration. Let's start with a definition in the form of an equation. Our definition for acceleration is change in velocity divided by the length of time it took to make that much change in velocity, and we call that, and actually an average acceleration in exactly the same way that change in location divided by the length of time it took to make that change is average velocity. Just as velocity measures the rate at which location is changing, acceleration measures the rate at which velocity is changing. Okay? How many meters per second of velocity change do you get per second? Just as here, it's how many meters of location change do you get per second. They're very similar things. A lot of the things that we said about velocity, we are also able to say about acceleration. For example, imagine we have a graph of velocity versus time. Just a simple graph where the velocity line is a straight line, and let's calculate the slope of that line. So you pick 2 points on the line, an initial and a final point, which defines some kind of time interval while we were watching the motion of this thing. And at the initial time, there's the value of the initial velocity. And at the final time, there's the value of the final velocity. And we know how to calculate slope. Slope is just the amount of change we get in the y variable minus the amount of change we get in the x variable, the horizontal variable. So change in y variable is just final minus initial velocity. Remember, whenever we talk about change, it is always final minus initial velocity, divided by change in the horizontal variable, which is just final time minus initial time. And of course, we can write that quotient in a simpler way. Final minus initial velocity is just what we call change in velocity. Final minus initial time is just what we call the length of time during which we had this much velocity change. But we just saw this same quotient a minute ago. It's average acceleration. So the moral of the story is, in a velocity versus time graph, slope is acceleration. In a velocity versus time graph, slope of the velocity line tells you what the acceleration is. Exactly the same way that in a position versus time graph, slope was velocity. In the position versus time graph, slope of the position line tells you the rate of change of position. Rate of change of position is what velocity is. In the velocity versus time graph, slope gives you the rate of change of velocity, but rate of change of velocity is just what acceleration is. So you see, there are a lot of parallels between acceleration and velocity because they're both measuring the rate at which something changes. So let's look at just one example of this idea. In a velocity versus time graph, slope is acceleration. And here's our velocity versus time graph. And measuring time in seconds and velocity in meters per second. Let's say we initially have a speed of 10 meters per second, but after 1 second it has slowed down to a stop. And then during the second, it's going to be moving in the negative direction, and the velocity will change from 0 to -10. And then in the third second, the velocity will change from -10 to 0, like that. And then in the fourth second, the velocity will change from 0 to +10. So what does the acceleration versus time graph look like? Mark off 1, 2, 3, 4 seconds. And in the first 2 seconds, this line is straight, which means the slope is the same everywhere along that line. So constant slope, and it's a negative slope. Since slope in a velocity versus time graph is acceleration, constant negative slope means constant negative acceleration. The velocity is always becoming more negative, and it's always doing so at the same rate. Well, we can actually calculate the value of this negative acceleration. In these first 2 seconds, the acceleration is just goes from 10 to -10. That is the final value of velocity is -10 meters per second minus the initial value, which was +10 meters per second. And the length of time it took to make that much velocity change was 2 seconds. So you have -20 over 2, or -10. -10 what? -10 meters per second per second. And we can write a unit label of meters per second like this, as if it was meters per second squared. What this really means is that in each second, the velocity gets 10 meters per second more negative. Okay. In the first second, it went from +10 to 0, and then in the second second, it went from 0 to -10. So the acceleration for the first 2 seconds is -10, and that's in units of meters per second per second. Then a different slope from 2 to 4 seconds. It's a constant slope and positive. On a velocity versus time graph, slope is acceleration. So a constant positive slope means constant positive acceleration. And we can calculate the value of that constant positive acceleration. The value of this slope is the value of the acceleration. And from 2 to 4 seconds, the velocity changed from -10 to +10. So the final velocity was 10 meters per second minus the initial velocity, and the initial velocity was -10 meters per second. So minus the initial velocity means minus 10 meters per second. And it took 2 seconds to make that much change. So now 10 minus 10, that's 10 plus 10, or 20. 20 over 2 is plus 10. Plus 10 meters per second. In each second, the velocity gets 10 meters per second more positive. From 2 to 3 seconds, the velocity went from minus 10 to 0, got 10 meters per second more positive. And from 3 to 4 seconds, the velocity got 10 meters per second more positive. It went from 0 to 10. So from 2 to 4 seconds, the acceleration is positive 10 meters per second. In the first 2 seconds, it was negative 10 meters per second. The absolute value of this acceleration is the same as the value of this acceleration because these two lines were equally steep. And we'll practice with this a lot more over the next